Hello everyone. So for CS390 NIP today, we are going to be discussing reinforcement learning. This is going to be kind of a short lecture just to tide you over as you're working on your final project and stuff. Eventually we will be having the ethics lecture, which is going to be a little bit of a bigger one. But this is just, if you want to learn a little bit more about reinforcement learning, which is the kind of research I do, so I have a little bias here. This will be about that. This is going to be a very summary video. It's not going to be in depth at all, but it should be kind of interesting, and it'll show you how to write a very basic reinforcement learning algorithm. By the way, this has almost nothing to do with image processing. You can use image processing in this, but even my example has no image processing involved, so that's why this is not a more prominent part of this, but it'll still be cool. This will be a fun little sojourn. So let's get started. So our inspiration for this, or the inspiration I will pose to you for this, is that our code is bad and we should feel bad. So back in NIPS 2017, Peter Abil, he did this, he made this little video he showed us. I don't have the sound on, but you can see this robot here. It's doing it's going to do all sort of tasks, all these crazy tasks. Like, look at that, it's sweeping, it can pick up stuff, it can do all these things humans can do. It can use the vacuum, it can clean things. It can do all sorts of different things. But here's the secret that they reveal partway in. This robot that is doing all of these cool sci-fi activities, like opening beer, it is remote controlled. It is not autonomous at all, which was the point. The point is, our hardware is there. Our hardware is ready for all of this crazy stuff. We've gotten to that point. What we haven't done is created code that can make all of this autonomous. We have the body of the robot, of the crazy sci-fi robots. We don't have the brain yet. And that is the gauntlet that is thrown for us to pick up. And reinforcement learning is sort of a attempt to pick that gauntlet up. So, what is RL? RL, or reinforcement learning, is a field of machine learning, and specifically AI, directed at understanding and solving general tasks that follow a particular model. And that model involves an environment and an agent. We'll get a little more into that in a moment, but it's considered the third major paradigm of machine learning. So we've talked about supervised. Classification is a great example of that, where we have our labeled data and we're trying to do something with that data. We're trying to put labels on that data, and we train it with already labeled data. We also have unsupervised learning, where we are given this data unlabeled, and we have to learn things about it without any sort of help, basically. Finally, reinforcement learning is kind of different from either of those, but it involves this environment-agent setup. There is no labeled output pairs like we have in supervised. Instead, the high-level idea is we're trying to have an agent that balances exploration of the environment, searching for knowledge, learning about the environment, and exploitation of the environment, using the environment to using that gained knowledge we figured out earlier to gain reward is the term. So this little diagram here is probably the quintessential diagram for reinforcement learning. We have an agent. That agent outputs an action. The action goes into the environment and changes the environment. And the environment then outputs both a state, which is going to be fed back into the agent, and a reward. that is also going to be given to the agent. Now, if you wanted to segment it a little more, you can think of the environment and the reward as a separate thing, where the reward is getting that S+1 from the environment and generating the reward. A reward function is doing this. And we'll often talk about reward functions being the sometimes implicit, sometimes explicit function of the environment that's determining what reward the agent gets. But this is the standard, this is the idea we're going for. We have an agent that is taking actions in the environment, that is changing the environment, creating a new state for it, and generating a reward. The important thing to realize too about the reward, that is going to determine the behavior of our agent. We're going to use that reward. The entire goal of the agent, basically, is to increase that reward. It's the opposite of a loss function. We're not trying to minimize it, we're trying to maximize it. So, let's talk about what reinforcement learning can do before we get into the nitty-gritty of it. And this is kind of a fun part. You can do that. So I love that. He's just running across there. He's just going. Look at him. It's like half of a Naruto run. It's great. We got this guy. He just gets up. His entire job is to stand up, and he does it. He succeeds. This is the best one. Oh, look at it go. It's going under things. It's jumping. It's great. I love that thing. I don't know what it is, but it's just a running thing, and I love it. Okay, so we have... Oh, and the spider. You need a jumping spider. You can't do reinforcement learning without a crazy little jumping spider thing. But yeah, this is the kind of stuff we can do with reinforcement learning. But, you know, it's not just that. You could do, like, Atari games, or... Here's a kind of like a stripped-down Pac-Man. And see, it even figured out that once it gets that, it can go turn around and eat the ghosts. Yeah, so it can play these old games and stuff. Because, you know, as long as you have reward, which we can get from score down there, and as long as you have the environment, which in this case, it's just reading the screen, taking that in with some convolutional layers, and there you go. Hey, there's our image processing. Right in the Pac-Man. You can do the same thing with the Brick Break. That's a pretty good game there. Again, we have a reward function, the score, and we have our environment. And this is a neural net that is doing really fairly well at Brick Break. It's not doing that well. I've seen better. I don't know how well this one does eventually, though, because it's just a GIF. This is the most famous one for sure, because this is kind of recent. Go, AlphaGo. AlphaGo is a DQN. This is an algorithm that we're going to learn later in this lecture. It's a reinforcement learning algorithm. And AlphaGo was able to just mop the floor with humans using it. Some pretty crazy stuff. We can put it in cars, make it drive stuff. The score function is not hitting things and getting there at a good speed. It's a pretty complex mixture of the two. Now, there are some horrific safety concerns and ethical concerns, and we will talk about that in the ethics lecture. But, you know, you can. And I've done it with simulators. That's kind of fun. Fun story with reinforcement learning. And this kind of speaks to the black box nature of, you know what, actually, I'm going to save that story. I'm going to save that story for the ethics lecture. But, no, I'm not going to save that story. I don't have that. I'm going to forget. So, fun story here. I don't remember who told me this for sure. I think it might have been Anthony. Did Anthony tell me this? I don't know. Someone told me this. Don't know exactly how true it is, but the idea is pretty true. You had a car. It was driving. It was I think it was a simulated car probably, and it was driving with a reinforcement learning algorithm, and they had gotten it to go around in cities very easily. It was driving around the villages and it was doing great. What happened, though, is as soon as it went over a bridge, it immediately swerved off the bridge into the water. So they tried to figure out what was going wrong with this. They thought they had trained the neural net so well. So they check their saliency maps and everything. They look at what information they can using the weights they have. And what they figure out is the AI is looking specifically, very heavily, for two large strips of green color, right along the sides. What it turns out it had figured out was that it could find where it was in the road based on the grass on the side of the road. So, when it had driven over the bridge, it couldn't find any grass, so it didn't know where it was on the road, so it had to go find some grass. So it drove right off the bridge. So that kind of demonstrates first of all, the black box issue with neural nets. You don't know exactly what it's doing internally because you're just running gradient descent and hoping it finds a good solution, and one that you'd expect it to. And it also shows the danger of these corner cases. But we'll get into that debate, that discussion in the ethics lecture. So let's talk about the algorithm we're using here. This is something called Q-learning. We're going to have a few definitions. We have, first of all, a policy function. We have a policy function that is going to take in a state and at a time, so S of t, and it's going to output an action that the agent does. Sometimes we will explicitly write that, and the neural network will be trying to model the policy function. But in this case, that's not what we're doing. We're going to define something called a Q function, also sometimes called a quality function. That's what it stands for, but usually we just call it a Q function. This is going to take a state, S of t, and an action, A of t. And it's going to return the expected value of that, expected value in terms of reward, of taking that action t given state t. And it should take future rewards into account. So it's not just going to figure out what moving from space A to space B is going to do for us. It's going to say, alright, well, if I move from space A to space B, next turn I can go to space C. So it should take that into account too. It's supposed to try to understand future rewards going into the future all the way until whenever. And that function is usually, the idea of this function is going to be, it's the expected discounted reward, cumulative reward, given the state in the action. In this case, you can think about that as reward t plus 1 plus reward t plus 2 times some discounting factor. That gamma there is going to be some usually fairly large probability. You might make it 0.95 or something, even 95%. And then the expected value is going to be RT plus 1, the reward at the next time step that we're expecting, plus the reward at the time step after, but we cut a little off because it's in the future, we're not sure about it, there's probabilities involved, so we have that gamma value. And it's going to get, that gamma value is going to stack on top of itself more and more as we go into the future. So we care much more about rewards soon. But we do care about future rewards. And that function, that e of RT plus 1 plus gamma RT plus 2, yada yada yada, given state t and action t, that is what we are modeling with our neural net. Important to realize that, because that means we know exactly what our inputs for the neural net are going to be. Whatever information we get from the state, plus our action. or sometimes we build that into the architecture or action so we can calculate all of them at once, but don't worry about that. The basic idea that we're building in is we give it state and action, and it is going to return a reward. This is where, if I was giving this as not an online lecture, I would ask the question of you guys, what is going to be the last activation of our Q-learning neural net? And the answer to that is going to probably, unless the reward is kind of weird, is going to be linear, because the reward is usually going to be a number just between negative infinity and infinity. We want to make it as big as possible, of course, but as this is trying to output a reward, we need to make sure that last activation fits it. So it's just going to be a linear activation, or no activation if you want to think of it like that. So yeah, how do we... I changed these slides around so that doesn't make as much sense, but yeah, the question is, how do we make this? And I already answered that for you. Neural nets. Well, you can really use any machine learning algorithm as long as it can do the job of predicting their words. But neural nets, because those are more fun, and that's what this class is. So, of note also, we've been calling this Q-learning. If we use a neural net to do it, we can now call it a DQN, a Deep Q-learning network. And that's nice, because everyone wants to unlock prestige classes when you're playing RPGs. And life's an RPG. And we get to unlock the DQN. Yay! So, what task are we doing? Well, this is a task that's using control systems a lot. You'll notice that most reinforcement learning ends up being done on things that model applies to very well, where there's a clear environment and a clear reward. And the two biggest domains for that are control systems and games. So you'll see a lot of things like Atari game DQN or Nintendo game DQN, and you'll also see a lot of, here's this control task that we've been doing for years in control systems, but we're going to have a neural network do it instead of having a complex series of filters and waves and garbage. So this is pull cart. It is a pull that is on a cart. That is the long and short of it. We have this cart. It can move laterally back. Yeah, it can move laterally back and forth. The pull does not attach to a motor or anything. It starts in the upright position, but it can totally just fall down. And what we want to do is move the cart to keep the pull from falling over. We're using our lateral movement to stop the pull from falling. We do have sensors that are telling us what position the pull's at, what speed the car is going, all of that. We get the angular velocity. We get all the information that most control systems get for this, except instead of using fancy math to try to get a solution, we're using a neural net. So we're going to start our code here. We're going to create this class, a DQN agent. We have these variables, these xbreak, xdecay, xmin. Exp in this case is going to stand for explore, and these are going to determine what our decay is going to be over time for our exploration. We also have our gamma. We talked about that a little bit. In this case, we have gamma is going to be 95 or 95%. We have learning rate, just like we normally do with neural nets. We have this memory, which we'll talk a little bit more about this, but as you can see, we set it to be a deck that has a maximum length. In this case, it's a pretty big one, though. It's 1 million. It will only hold 1 million objects, and any time if we end up with over 1 million objects in it, it'll start dropping things basically at the end. And of course, we have down here our neural net. This is using Keras, just like we have before. We've created the sequential network, ReLU linear. Of course, we have to end in linear so it can tell us what our weights are going to end up being, or our rewards going to end up being. We've also set our observation space and our action space. In this case, we are not going to be passing the neural net what action we're taking. We're going to give it the state, all the state information. In this case, we're calling it an observation. Um, but we are not going to pass it the action. Instead, we're going to have basically a different head for a different neuron for every action, and all at once we're going to calculate our expected reward if we take that action. Which is nice doing it that way, because then we can just take an argmax of that, and that is our action. That's the action we take, whatever number that ended up being. Yeah, we're compiling with MSE loss, because why not? MSE works well here. Atom optimizer works fine here. I actually did a quick study into what optimizers are best for reinforcement learning. Atom's pretty good. This isn't like full yet because we haven't quite finished it, but it looks like early on, SGD, if you just do stochastic gradient descent without really worrying about Atom even, but you make sure that it has momentum, it has like 0.9 momentum or whatever, that'll do really well for most reinforcement learning. But Atom does the job here. Specifically with that, the SGD will make it a lot more stable a lot of the time. But that's just my early testing. Could be wrong. It's the results we have so far. So here's going to be our little function to decide how we act. We take in our state. You can think of this entire thing as our policy function, by the way, even though most of it isn't as a neural network. It's just using the neural network. What we do is we roll a die, have our random number generator go, and if our random number is less than our exploration rate, which at first, you saw how we do this decay, at first our exploration rate is very, very high. So most times it's just going to explore. And as we go down, it's going to get lower and lower and lower until it's very small. And at that point, it's not going to do much exploring. It's mostly just going to be acting on itself. So in this case, we have our exploration set. If we go inside of this loop, of this if statement, then we just pick a random action. We aren't even going to do the action that the neural net says. We just pick some random action, we're done. If we don't explore, however, we're going to do our predictions to find to figure out what our best reward is, and then we just pick the argmax, pick the best possible reward. And that's it, that's the whole thing. We have the neural network predict what our best reward is going to be, and then we pick that action. Pretty simple. We're going to have this remember function. This is just going to be called every single time we take an action and get a result back from that. This is going to take in the state, the action, the reward we got from taking that action, and the next state that came back from that, as well as if it ended up being terminal, if that ended the game, whatever the game was. By the way, there's a difference between offline and online learners. So an offline one is going to learn after the game. It's going to play the game how it is, and then it's going to go, oh, okay, let's do our back propagations now, and we'll learn at this point. Online is going to keep learning as the game is played, and that means you can have a game that doesn't terminate. But in this case, we're allowing for the ability to terminate, to train it offline or online. Next, we have experience replay. So, the problem, we were talking about the online versus offline. If we're training online, we're going to have a very strong temporal relationship between the data we're getting in and how well we did. So, if we are currently doing something, we're currently taking a few actions that we're going to label as action set A or whatever. that is going to have a major effect, a major correlation on how well we do. And we don't necessarily want our neural network to be so based in the now. We want it to be based on what it's learned before, all of that. We want to decouple our learning from what our neural network is doing right now. So we use this algorithm called experience replay. What it's doing is we have our memory that we had in that deck. We're going to randomly sample it to get a batch. So we're going to be getting something, we might be getting some data points that are happening right 5 minutes ago in the algorithm. This might be things that happened way, way, way before, like right at the start of training. This might be things that happened, literally the last movement was this. It's completely random. We sample that, and with that sample, we're going to train our neural network. We have our predicted reward. We find that from what reward we actually ended up getting. And we do our training with self.model.fit like we normally do. And that's it, basically. Yeah. By the way, this is not the best DQN you can make. There's a lot of improvements to make this better. But this is a very simple DQN that will do the job for this pull cart task. Also, another note, for our pull cart task, our observation, I think there's only 4 sensors on it, so it's just going to be 4 doubles coming in, basically. Last thing to note probably is, here's where we actually do our experience rate decay. We have the experience rate go down by multiplying it by how much decay we have. I think that was 99% or something, so it's going to go pretty slowly, but it's always going to be above a minimum, because once we stop, if we were to have it at 0, then we're just not learning anything. We're just continuing to reinforce what we have, basically. Unless there's randomness in the environment, which often there is. But the experience rate is definitely, usually you don't want to keep it, you never want to have it go to full 0. You want it to go to some very small number. And unless you're testing. You're going to have, you want to have zero explore when you're testing, because then you're doing your testing. You want to see how well your neural network did. So let's see the results we end up getting with this. So yeah, it does a pretty good job. You can see it started over there just because it stayed up so long that it stopped it. There's a maximum reward it can get, which is just if it stays up, it times out, basically. And you see it's learned to mostly not move, but just take these little tiny shifts to keep it balanced. It's done a very good job. Yeah. I think I got rid of most of this, but a lot of my research was working on this for a while. That little runny guy, he goes really fast. Yeah. My research with this is mostly to do with stability, first of all. Making these algorithms run in a way where they're going to be able to do it consistently instead of just every once in a while it does really well and gets a high reward. And the other thing is being able to learn continuously. Being able to keep learning without hitting some sort of breakpoint, and getting continuously better at the task by increasing the understanding and increasing the actual size of the neural network as you go. And that's trickier than it sounds, because you can't really just keep throwing pieces at the end of the network. That tends to not work very well. I use something called a progressive net. If anyone's interested in learning about prog nets, then I can talk about that at some point, but throw it up on Piazza and we'll see. But yeah, this was reinforcement learning, and that's that. have a good day. Keep working on your final projects. We had a problem the other day where we didn't get most of the people sending in their final project charter. So do that. Please do that by Wednesday. I said on Piazza, I'll extend it till then, but after that, we're just, your grade's going to depend on what you sent in. So, yeah, please turn that in. And that's that for today. Everyone have a great day.